Okay, so taking a look at lesson 3. So in the last lesson, we continued to talk about quadratic functions, where we looked at it in general form, where f of x or y is equal to x squared plus bx plus c, where a, b, and c can be any real number as long as a is not equal to 0, otherwise it won't be quadratic anymore. The graph is going to be in the shape of a parabola, so a symmetrical arch opening up or down. It's got a maximum point, or opens down, if a is less than 0 or a is negative. It has a minimum point, or opens up, if a is greater than 0. The vertex is going to be the actual coordinates at the maximum or minimum point, and the maximum or minimum value of a quadratic function is the y value at the vertex. So if I ask what the maximum value is or the minimum value is, it's just the y part from the vertex. So if we're taking a look at a function where we have one is f of x is equal to x squared minus 6x plus 11, and the second case is g of x is equal to bracket x minus 3, close bracket, square it, and plus 2. When I graph out both these functions on my calculator, the funny thing is I can only see one line because they overlap or appear to be the same. If I expand the second equation, or the g of x, then I'm going to say that, well, g of x is equal to x minus 3 squared is the same as x minus 3 times x minus 3, and then plus 2. X minus 3 times x minus 3 is going to give me x squared minus 6x plus 9 plus 2. And when I combine the like terms at the end here, then I'm going to say that g of x is equal to x squared minus 6x plus 11, which is the same as what f of x was. So f of x is equivalent to g of x. They're just two different equations, or two of the same graph, that are in different forms, so the equations look different. In the second one, I see I have y is equal to negative 3x squared minus 30x minus 77, or y is equal to negative 3 bracket x plus 5 squared minus 2. When I graph them out, the same as last time, they appear to be the same. When I expand out the second equation, then I can say that y is equal to negative 3 x plus 5 squared is the same as x plus 5 times x plus 5, and then minus 2. Or y is equal to negative 3, when I square out the x plus 5, or FOIL it out, I get x squared plus 10x plus 25 minus 2, and then I need to multiply that by that coefficient of negative 3, so I'm going to say that y is equal to negative 3x squared, and then the 10 times negative 3 is going to give me negative 30x, and the 25 times negative 3 is going to give me negative 75 minus 2, and then I'm going to combine those like terms again. Y is equal to negative 3x squared minus 30x minus 77, which is the same as what the first equation was. In the first case, we had our general form, and now we have what's called our standard form or vertex form, because we're going to be able to pull the vertex easily from this equation. The vertex form is in the form of f of x is equal to a bracket x minus h squared plus k. So, in the table, we're going to complete the following using our graphing calculators. For the first one, I see that the coefficient of x squared, or whatever is squared, is just going to be 1, which means I have an a value of 1. I don't have any number inside the brackets, and I don't have a constant at the end, which means the other 2 points are going to be 0 and 0. When I graph this out, I get a vertex at the point of 0 and 0. In the second case, I have this imaginary one where a is. I have an h value of positive 2, because we got to be careful. If the original equation is x minus h, and this says x minus 2, then the h is actually just the 2 that comes after the minus sign. And I don't have a constant at the end, so that'd be the same as a 0 at the end. This gives me a vertex at 2 and 0 when I graph it out. For the next one, a has a value of 1, and the h value is actually going to be negative 4, even though it looks like x plus 4 squared. Because it's minus h, that would actually be the same as x minus negative 4 squared. And the plus comes from the double negative. And still no k value at the end, so I'm going to wind up with 0. And I have a vertex at negative 4 and 0. For the next one, I have an a value of 1, I have an h value of 2, and now for the first time I have a k value, which is going to be this negative 3 at the end. Because it says plus k, I keep the same sign. I don't flip the sign like I did with the h. So I wind up with 2 and negative 3, where my vertex is. In the next one, a is 1, h is negative 4, k is positive 5, and a vertex at negative 4 and 5. For the next one, I have an a value of 6, an h value of 2, and a k value of negative 3, and the vertex occurs at 2 and negative 3. And the last one, because it just says minus beside the brackets, it's actually negative 1 for a, negative 4 for h, and positive 5 for k, and the vertex is at negative 4 and positive 5. If I'm to make up a few of my own for these, then I can just play around with the different values. So in this case, I'll say, okay, well, what if I had y is equal to, x squared plus 5, where I just add a k value, but I don't change a and I don't add an h value. Or y is equal to negative 2 x plus 1 squared, y is equal to x minus 5 squared plus 5, or y is equal to negative bracket x plus 3 squared plus 1. Well, here I have a is 1, h is 0, and k is 5. I have a vertex at 0 and 5. I have an axis of symmetry with that imaginary vertical line when x is equal to 0, and this one opens up. For the second one, a is negative 2, h is negative 1, k is 0. I have a vertex at negative 1 and 0, and the axis of symmetry occurs at x is equal to negative 1. This one opens down. The next one, I'm going to have A is 1, H is 5, K is 5. A vertex of 5 and 5. Axis symmetry is x equals 5. And this one opens up. And for the last one, A is negative 1, H is negative 3, K is positive 1. Vertex is at negative 3 and 1. Axis symmetry at x is equal to negative 3. And this one opens down. So, the pattern that I'm seeing here, well, A, just like it was in our general form, is going to determine whether it opens up or down. When A is positive, it opens up. When A is negative, it opens down. The vertex always occurs at the values of H and K. And the axis of symmetry is consistently x is equal to H, or the x value at the vertex.